Welcome to This Explainer. Today, we're diving into the deep architecture and, quite frankly, the practical magic of Python's unittest.mock library. Look, if you've ever spent hours, literally hours, chasing down a failed test, only to realize an external API was just temporarily down, well, you're exactly in the right place. Today, we're going to learn how to completely master code isolation and stop those flaky tests dead in their tracks. How? By figuring out exactly how Python's mocking engine actually works under the hood. Okay, let's take a quick look at our roadmap. We'll be hitting the art of code isolation, checking out the taxonomy of test doubles, peeking inside Python's mocking engine, mastering the patch decorator, and wrapping up with some real-world mocking best practices.
All right, let's jump right into part one, the art of code isolation.
I want you to really think about this for a second. Are your tests actually testing your code, or are they just testing your network latency? It's a tough question, right? Because external dependencies, things like remote databases, third-party APIs, even your local file system, they introduce a massive amount of unpredictability. When you bake those into your unit tests, you're not really writing unit tests anymore. You're writing unstable, slow integration tests. I mean, think about it. If a third-party payment gateway goes down, your test fails. But your actual application logic, it might be perfectly fine. So, how do we fix this? We use code isolation. This is basically the practice of completely decoupling your system under test, we'll call that the SUT, from those messy external boundaries. Think of code isolation kind of like an illusionist's trick. We use specialized tools to create this perfect stage magic environment where our system completely believes it's operating in the real world. It thinks it's hitting real databases and real networks, but in reality, it's interacting with perfectly controlled stand-ins. This guarantees that when a test fails, it is 100% because of an internal logic error, not some weird environmental glitch. Moving on to Section 2, the taxonomy of test doubles. Now, in software testing, we rely on a whole family of simulated dependencies collectively known as test doubles. And it is absolutely crucial to understand the differences here because confusing them will lead straight to brittle tests. Take a stub, for example. A stub simply spits out a hard-coded, predetermined response, like a canned JSON string. It's simple. A mock, on the other hand, is way smarter. It's a pre-programmed object that actually records how it was used, which lets you validate expectations later. So, rule of thumb, if you just need a quick canned response, use a stub. But if you need to prove that, say, a specific internal method was called exactly twice with very specific arguments, that's when you bring in a mock. Interestingly, this brings up a massive philosophical divide in the test-driven development world about how often we should actually use these doubles. On one side, you have the Detroit, or classicist school. They prefer checking the final state of the system and use mocks very minimally, usually just for external I/O. The upside? High resilience to code refactoring. On the flip side, we have the London, or mockist school. They focus heavily on interaction verification, pretty much mocking every single collaborator outside the system under test. This gives you incredibly isolated test environments, but it tightly couples your tests to your underlying code structure. Python's tools totally support both, but you really need to know which philosophy you're actually deploying. Which leads us nicely into Section 3, inside Python's mocking engine. Okay, so unlike traditional mocking frameworks in languages like Java, where you often have to strictly record all your expectations before the code even runs, Python's unit test mock uses a super dynamic action and assertion model. Thanks to Python's wild metaprogramming capabilities, specifically how it intercepts lookups using the _getter@_dunder method, Python mocks act as these dynamic, on-the-fly containers. If your code accesses a method on a mock that doesn't actually exist, the mock doesn't crash. It just casually creates a new child mock, registers it, and returns it. After all the action is done, you then step in and make explicit assertions about what just happened. It's incredibly flexible. To actually wield this engine, you've got a whole toolbox of classes at your disposal. You've got the base mock class for standard functions. Then there's MagicMock, which is awesome because it comes pre-configured to easily handle Python's magic dunder methods like _len or _iter. Working with modern asynchronous coroutines, no problem. Async mock is natively built to handle await keywords without blowing up your test loops. Then there's non-callable mock, which is perfect for static data objects. It'll actually raise a type error if your test accidentally tries to run it like a function. And finally, for concurrent execution blocks, threading mock has your back. But hey, all this dynamic flexibility, it comes with a pretty big hidden danger. Since standard mocks dynamically create attributes on demand, Think about what happens if you just misspell your assertion. What if you accidentally type assert underscore called with instead of assert underscore called with? Well, a purely dynamic mock would just shrug, create a new child mock named assert, and your test would silently pass, even if the code is completely broken. Thankfully, the engine has a brilliant safety net called the unsafe attribute guard. It actively watches for common typos of the word assert and throws an attribute error to stop those silent failures dead in their tracks. To take that safety even further and prevent fragile tests, you really need to lean on structural constraints. Look, dynamic mocks are great, but if they accept method calls that the real production object wouldn't, well, your tests are basically lying to you. By using the auto-spec feature, Python will actually recursively inspect the real target object and constrain the mock to perfectly match its API. It enforces exact method signatures, keyword parameters, and it will even yell at you if you pass the wrong number of arguments. Fun fact, as of Python 5.2.0, AutoSpec even natively supports data classes, keeping everything strictly aligned with your production boundaries. Let's keep moving. Section 4, Mastering the Patch Decorator. All right, listen closely. If you take away just one single golden rule from this entire explainer, let it be this massive concept about Python's namespace resolution. Patch where it is used, not where it is defined. Seriously, write that down. This is, without a doubt, the #1 stumbling block for engineers learning to write mocks in Python. Let me break down exactly why this trips people up. When you import a function into a module using from database import query database, Python creates a direct local binding right there in that specific module's namespace. If you try to patch the original database.query database definition over in its home file, your system under test is just going to completely ignore your mock and keep calling the unpatched local reference. You absolutely have to patch the reference based on how it was imported. If it's a direct binding, patch the importing module. If they just used import database, then you patch the origin module directly. Mastering this one namespace rule is going to save you so many hours of head-scratching debugging. Okay, so once you target the right namespace, patching always follows a highly predictable 4-step lifecycle. Step 1, you temporarily replace the target namespace with your mock. Step 2, your system under test does its thing and interacts with the mock. Step 3, you swoop in and make your assertions, validating stuff like call count. And step 4, you stop the patch and clean up, restoring the original object. Whether you're using the @patch decorator, a context manager with the with statement, or the super handy mocker fixture in PyTest_mock, this underlying lifecycle is exactly the same. It ensures you never leave lingering mocks that pollute memory and ruin your other tests. And that brings us to our final part. Section 5, Real-World Mocking Best Practices. Let's talk application. These are the absolute high-value areas where you should be deploying unittest.mock to turbocharge your continuous integration pipelines. You want to simulate JSON payloads so you can test parsing logic without waiting on network latency. You want to fake database queries, so you aren't spinning up a live SQL server just to test a simple data transformation. You can bypass slow, clunky file system reads entirely. You can even mock out Selenium's explicit WebDriver wait classes. That means you can validate complex UI interaction logic instantly without the massive overhead of launching an actual headless browser. It's a total game changer. But of course, you've got to watch out for the traps. As we just went over, targeting the wrong patch path will ruin your day. Failing to reset mock call histories between shared test cases, that's a one-way ticket to cross-contamination. Also, a lot of folks forget that you can use the side effect attribute to simulate severe network exceptions, not just return happy path data, so test those edge cases. But the biggest pitfall of all, over-mocking. If you mock every single internal class, you bloat your codebase, you tightly couple your tests to implementation details, and you create a suite that is an absolute nightmare to maintain when you try to refactor later. So it's all about striking a careful balance. You want to rely heavily on mocks to create fast, deterministic, and isolated boundaries around the very edges of your system. Stuff like the APIs, the databases, the file systems. But at the same time, you should really aim to keep your core domain logic entirely unmocked. Let your internal classes actually talk to each other in your unit tests. That is how you get true, reliable behavior validation. Which brings us to the core reality of automated testing. Master the engine, understand the namespaces, and isolate intelligently to keep those CI pipelines blazing fast. But as you build out your suites, I want to leave you with this final provocative thought. Are your tests genuinely proving your core application logic works, or have you mocked so deeply that you're really just proving your mocks work? Keep that balance in check, write smarter tests, and thank you so much for joining me for this explainer.